Welcome to AI Peer Review. Today, we're diving deep into a really interesting paper, YOLO-World, Real-Time Open Vocabulary Object Detection.
Yeah, this one's definitely for you technically savvy folks out there,
Yeah.
especially if you're following computer vision. It's a fascinating look at how they're taking the efficiency we know from YOLO
Right, the speed.
and stretching it significantly to detect objects way beyond just a fixed list.
Exactly. We're going to unpack the fundamental problem with traditional object detection, right? That fixed vocabulary.
Mhm.
You train it on COCO, maybe 80 categories, and that's its world.
That's it, which, as you know, isn't how the real world works. It just throws curveballs.
Constantly. So that's the challenge YOLO-World tackles head-on, these open-world scenarios. Our mission today really is to get into the core innovations.
Yeah, the reparameterizable vision language path aggregation network, REP-VLPAN for short, thankfully.
Ah, yeah. And the region text contrastive loss. Plus, that whole prompt then detect idea, which sounds intriguing for actual use.
Definitely intriguing for efficiency.
Okay, so let's start there with the bottleneck, the fixed vocabularies.
Right. So as you said, traditional methods learn a closed set, cars, people, dogs, whatever's in the training data. Once that training's done, the detector's kind of locked in. It only sees those things.
Which really limits where you can use it effectively. I mean,
Yeah.
think about dynamic environments.
Exactly.
Yeah.
Imagine a security camera. Your standard detector might see a person or a car. Fine. But what about, I don't know, a scooter left somewhere or a drone flying by? If scooter or drone weren't in the original 80 categories.
It's basically invisible to the system.
Pretty much. It's blind to it.
It's like, yeah, trying to understand the world having only read one specific manual. And people have tried using vision language models for this, right? But there were issues.
There were, yeah. Often it came down to, well, finding enough good training data that covers everything. That's hard. And the computational costs, these models can be really demanding.
Right. Building robust open vocabulary detectors often meant needing serious hardware. So let's bring in YOLO-World. How does it try to, sidestep these problems?
Okay, so YOLO-World's main aim is high efficiency in open vocabulary detection. It's not throwing out the YOLO playbook entirely. It builds on that standard fast architecture.
So it leverages the existing strengths.
Exactly. And the clever bit is integrating a pre-trained CLIP text encoder. Now, CLIP, as you probably know, has already learned a really rich connection between images and text.
Yeah, it understands descriptions.
Precisely. So YOLO-World uses that. It processes text descriptions you give it, and that lets it find a much wider range of stuff, even things it wasn't explicitly shown visually during its own training.
Okay, and that brings us to the core mechanism, the REP-VLPAN, Reparameterizable Vision Language Path Aggregation Network.
That's the one. This is where the magic happens, really, merging the visual side with the language side.
So it's based on the PAN from YOLO-8, but with some key upgrades for this cross-modal stuff.
Correct. Two main components stand out: the text-guided CS players and image pooling attention. If you look at Figure 4 in the paper, it lays out the architecture, how these fit in.
Okay, let's break those down. Text-guided CS player, what's its job?
So, after the main feature extraction part, the dark bottleneck, these layers use something called MAC sigmoid attention. Think of it like this. They take the text features, the understanding of the descriptions,
Right.
and they selectively inject that information into the image features at different scales, different levels of detail. It's like whispering hints to the visual part. Okay, look for something like this described by the text here and here.
Okay, that makes sense.
Yeah.
Guiding the visual search. And the image pooling attention, how does that fit in?
Right, so that works sort of the other way around. It takes the image features, pulls them down into smaller representative chunks, these 3x3 region tokens.
Condensed visual summaries?
Kinda, yeah. Summaries of different image parts. And these summaries are then used to update the text embeddings. It uses multi-head attention for that. So information flows both ways. Text guides the image analysis, and visual context refines the text understanding within that specific image.
And that reparameterizable part, that's key for speed during detection, right?
Absolutely key for efficiency. So imagine you have a specific list of things you want to detect your offline vocabulary.
Like in that factory example, robots, conveyor belts.
Exactly. You can pre-calculate the text embeddings for robot, conveyor belt, etc. And here's the clever part. YOLO-World can take those pre-calculated embeddings and essentially bake them into the weights of some layers in the REP-VLPAN.
Ah, so it modifies its own structure slightly based on the target words.
Effectively, yes.
Yeah.
The math is in Appendix A, Account 1 if you want the gory details. But the upshot is, the model doesn't need to re-encode robot every single time it sees a new image frame.
Because the understanding of robot is already embedded in its processing path.
You got it. That saves a ton of computation, makes it much faster for real-time use.
Okay, that's a neat trick. So that's the inference part. How does it learn this open vocabulary in the first place? The pre-training.
Right. The pre-training uses this region text contrastive learning approach.
Mm.
They train it on huge data sets.
Yeah.
And the core idea is transforming the usual training data, bounding box, plus a simple label like cat,
Yeah.
into pairs of an image region, the
Yeah.
box, and a richer text description. That could just be cat or maybe a fluffy white cat sitting.
So giving it more textual context associated with the visual region.
Exactly, enriching the signal. And during this training phase, for each training sample, especially these mosaic images they use, which are combinations of pictures,
Right, for robustness.
it builds this temporary online vocabulary from the nouns and the descriptions for that specific sample. This helps it learn associations across a really wide range of concepts.
Okay, so we mentioned it, but let's really focus on this prompt then detect idea. How does that offline vocabulary make inference so efficient in practice? You mentioned figure 2C.
Yeah, figure 2C shows it quite well. The traditional way, or even some other open vocabulary methods, might involve encoding the text prompt, say, person riding a bicycle, every time a new image comes in.
Which takes time.
It does. With prompt then detect, you decide your prompts, your target objects beforehand. You pre-encode them just once, creating this offline vocabulary tailored to your needs.
So my list of factory items or maybe road signs for an autonomous vehicle.
Perfect examples.
Yeah.
You encode those terms once. Then, YOLO-World uses that reparameterization trick we talked about. It absorbs those embeddings into its network weights.
Oh, great.
So when it sees a new image, it's already primed to look for those specific things. No text encoding needed on the fly for each frame.
It's like having the search terms pre-compiled directly into the search engine itself.
That's a good analogy, yeah. It leads to really significant speed-ups.
Makes total sense. So the performance numbers must reflect this. What did the paper show?
They're pretty impressive, actually. On the LVIS dataset, which is tough, it has over 1,200 categories.
Whoa, okay.
YOLO-World gets 35.4 AP, that's average precision, doing zero-shot detection, meaning it wasn't fine-tuned on LVIS beforehand. And critically, it does this at 52 frames per second on a V100 GPU. That's real-time speed.
That's fast for that level of open vocabulary performance.
It really is. Figure 1 plots this speed versus accuracy, and you can see how it stacks up well against other methods, many of which are much heavier. Table 2 gives you the full breakdown on LVIS zero-shot. It really hits a sweet spot between accuracy and speed, detecting things it hasn't explicitly trained on. At speed, that's the key takeaway.
Yeah, that efficiency is crucial. And they did ablation studies too, right? To figure out what parts were contributing most, tables 3, 4, 5.
Absolutely. Ablations are essential. Table 3, for instance, looks at the pre-training data. It shows that adding more diverse data, like from the GQA dataset, and even some image caption data from CC3M, using their pseudo-labeling method.
We'll get to pseudo-labeling later, yeah.
Right. Adding that data consistently boosted the zero-shot performance on LVIS, so diverse pre-training helps.
Okay, and Table 4 gets into the RepVL pan components, the text-guided CS players, and the image pooling attention.
Correct. And the results there are clear. Using both of those modules together gives a solid bump in accuracy, especially for the rarer categories in LVIS.
Ah, so it helps with the long tail problem.
Exactly. It shows their approach for fusing text and vision is working well, particularly for less common objects.
And Table 5 looked at the text encoder choice, CLIP versus BERT.
Yeah, and that was interesting. CLIP significantly outperformed BERT here.
Really? Why do you think that is?
Well, likely because CLIP was pre-trained specifically on image text pairs, huge amounts of them, so it has a better inherent grasp of that visual semantic link. Interestingly, they found that fine-tuning BERT during their pre-training helped it, but fine-tuning CLIP actually hurt performance slightly.
Huh. So the off-the-shelf CLIP embeddings were already pretty optimal for this task.
It seems so. Maybe further tuning made them too specialized for the detection pre-training data, losing some of that general-purpose power.
Fascinating. Okay, so it's strong in zero-shot, but what about fine-tuning it, like a traditional detector, on data sets like COCO or LVIS?
They tested that too. Tables 6 and 7 cover the fine-tuning results. On COCO, even when they simplify the model a bit during fine-tuning by removing the RepVL pan for more speed, it performs competitively with, and sometimes better than, standard YOLO models trained only on COCO.
So the pre-training gives it a head start, even for standard detection.
It seems to, yeah. And on LVIS, when fine-tuned, It significantly outperforms baseline YOLO-8 models that were trained directly on LVIS from scratch. Again, especially on those rare categories.
Yeah.
It really highlights how valuable that open vocabulary pre-training is, even if your end goal is detecting a large but fixed set of objects.
And it wasn't just bounding boxes, right? They tried instance segmentation, too.
That's right, Open Vocabulary Instance Segmentation, or OVIS. Table 8 shows those results. It demonstrates the architecture is adaptable. It can learn to predict pixel-level masks for objects, even novel ones, showing pretty promising results there too.
And the visualizations, figures 5, 6, 7, they really bring this to life.
They do. Figure 5 shows the zero shot on LVIS. You see it finding all sorts of things. Figure 6 is cool. It shows detection using custom prompts, like telling it to find a golden dog versus just a dog, or even dog with pointy ears. That level of detail.
Yeah, being able to specify attributes is powerful.
Very. And figure 7 shows referring expression comprehension, finding an object based on a phrase like the person wearing a red shirt. That opens up more natural ways to interact with vision systems.
Definitely. Let's just quickly touch on the underlying math for the technically minded. Equations 1, 2, and 3.
Sure. Equation 1 is for the text contrastive head, how it calculates similarity between visual object features and the text embeddings, using L2 norm and some learnable scaling factors. Equation 2 gives the formula for that max sigmoid attention in the text-guided CS player, how it weights the text info. And equation 3 details the multi-head attention used in the image pooling attention to update the text embeddings using those pooled visual region tokens.
And the overall pre-training loss combines a few things: contrastive loss plus standard box regression losses.
Yeah, section 3.4 lays it out. They use the region text contrastive loss, LTON, but also standard bounding box losses like IOU loss, LIU, and distributed focal loss, LDFL. Interestingly, they only apply the regression losses if the data source has reliable bounding boxes.
Acknowledging different data quality. Smart.
And that pseudo-labeling for the CC3M data you mentioned, Appendix B has the details. Basically, extract noun phrases, get rough boxes using another pre-trained detector like GLIP, then use CLIP to check if the box content actually matches the phrase.
A clever way to generate more region text pairs from cheaper image caption data.
Exactly. Filters out the noise, keeps the useful generative labels. It's a practical way to scale up.
Okay, so wrapping up. YOLO-World feels like a genuinely significant step. Efficient, real-time open vocabulary detection seems much closer now.
I think so too. They've shown you can blend YOLO's speed with vision language intelligence pretty effectively. The architecture choices, the pre-training, it all comes together to create a model that can see a much wider world without needing explicit training for every single thing.
And that prompt then detect paradigm, that seems incredibly practical, being able to customize and accelerate detection for specific needs.
Huge potential there, yeah. Flexibility plus speed, that's really appealing for deployment, especially on edge devices or anywhere real-time matters.
It's just amazing how this vision language pre-training can give even lightweight models such powerful open-world abilities.
It really is democratizing capabilities that used to require massive models. It opens up so many possibilities.
Definitely recommend you listeners check out the paper, especially the experiments and ablations, to really dig into the details.
Yeah, there's a lot more nuance in there.
It really gets you thinking, though. What are the killer apps for this kind of technology? Where could it make the biggest difference? And where does the research go next? How do we build on this? It feels like we're just scratching the surface of truly understanding the open world with AI vision.